and we'll go from current slide. Okay. I want to blame it on the jet lag from last week, but I completely forgot one of the preliminary things that I always do with every class, and I completely forgot it for my first two classes. I think I remembered it in my third class. I didn't have time for my fourth class, and the other two classes didn't meet at all, so I know we didn't do it there. And that was safety. Excuse me. Just think of the poor people at home. They weren't expecting that, were they? Okay, so let's go over this quickly because we need to get back to linear algebra. But this is one thing that we should, and we did talk about the syllabus, the research paper, and my what can I call it, office hours type thing. Here is one change to what we said last time. Last time when I came into the class, I was expecting to be canceled, but we had 5 paid students here, and I hated to cancel on that, so I said let's keep it. And we may have actually, I don't guess we added one more. My last class we added another student or two. This one we did not. But we are going to continue with this. But I also was holding out the possibility that one of my physics classes might have been not canceled but merged with another class. Well, as it turned out, the other physics instructor had a low class where I had one that didn't make. So what we did, we stacked both of those, and he's teaching both of them. So that does give me some office hours. None on Tuesday, Thursday, unfortunately. I have 15 minutes at the beginning of the day, 7:45 to 8, 10 minutes between classes, and I usually run down and swap books here at that time. 10 minutes between this class and the next one. I usually run down and swap out books then. And then I've got 30 minutes between the next two classes, except the fourth class is over on the Birmingham East Campus. That 30 minutes is eaten up by driving over there, so I don't really have any time left. But I do have this time. From 5:30 until 6, I'm going to stay on the Birmingham campus, Birmingham East Campus. I'll have office hours then. We probably won't do y'all any good unless you happen to be up on the Birmingham campus that late. I will have office hours there. Now, I didn't get that changed on my syllabi because I made that decision right at the end. I don't know if I'll get to make that change or not, but it's on my locator card. You'll see I have office hours there. All right. Now, on Monday, Wednesday, though, I have the 8 o'clock calculus class. So that's 4 hours. That goes from 8 to 10:40. Okay? Then a 20-minute break, big 20-minute break there. And then the second calculus class, Cal 2, starts at 11 and goes to 1:40. And since both physics classes have been taken over by the other instructor, we merged them or stacked them. Now, from, let's just say, 1:45 until 6 o'clock. Mondays and Wednesdays, office hours. So that's my big chunk of time. If you need to see me, if you need to call me, that's a good time to do it. Okay? Monday, Wednesday, 1:45 till 6. I'll be down around or in the office most of that time. I'll certainly run to the restroom or have to take something to an office or something like that. But generally, I'll be there. So that's the other big change. Now, safety. 3 areas of safety we need to think about. What are they? Weather! All right. Yes, they're here in Alabama. That's always a factor. This is our first named storm of the season. That's just a tropical, I guess it was a depression is all it got to, didn't it? Or did it become a tropical storm? May have been a tropical storm. But sometimes big old hurricanes will hit, and by the time they get up here, there's still tropical storms, and could be spinning off some tornadoes and other things like that. So we have to be wary of that. What happens if you hear that alarm go off? Wherever it happens to be, it sounds like it's in that direction somewhere. What do we do? Yes, this building doesn't have a basement, but you go low interior. That's what you keep in mind. Okay? And low and interior in this building, what that means, here we are in this classroom, the corner classroom up here. You go out to the hall, hang a left, go down this little half flight of stairs right here, and hang an immediate left out there, go down one more flight, and you're just about as low as you can go in this building. So when you come out that stairwell, you'll see right in front of your two restrooms. Those are not bad places to be in case of a weather emergency, okay? Because the walls are close together and you got lots of corners. That's where your strength of the building is. And the back wall back here is against soil. There is nothing else on the other side of the first floor down there except soil. So you don't have anything that can come crashing in. So that's a good place to be. Except it may not be much fun place to be for an extended period of time. And the other disadvantage of the restroom is no emergency lighting. There's a real good chance with severe weather, you'll lose power. So you cannot want to be in the bathroom in the dark. Okay, if you don't, then another, probably another good possibility, and more exciting than that, she's eating her breakfast too. Okay, tell her lunch or free lunch or whatever. So here's Warren. All right. Not much time for the classes, are there? All right. So the next best, or maybe even better, is the hallway. Now, the good news of the hallway, the walls are relatively close together. Okay? And the better news is emergency lighting in both ends. So if we do lose power, you can see. Okay? One of the sort of disadvantages, there are no corners. And corners are where the greatest strength comes. Okay? Another sort of disadvantage is you have the walls on both sides are just walls. You don't have soil on one side of them. So if you don't feel comfortable in the hallway, or if you want to be a little closer, right next to the restroom, and you have a couple of steps going down too, by the way. There is, underneath this corridor here, is on the first floor, is an academic dean's office. Now, she's not here all that frequently, but occasionally the associate dean will come over and use her office as well. And in the summertime, there's a summer enrichment program they do for high school students, and the guy who heads that up, when he's on this campus, he uses that office as well. So in the summer, it's probably occupied more than it is for the rest of the year. So if anyone's in that little office, again, close walls and corners. And the back wall is soil. Okay? So it's a safe place to be, but it's usually locked. But if it isn't locked, they let you in. Also has a couple of comfortable chairs. You might actually be able to sit comfortably. All right, next down the hall is a classroom. Now, classrooms are not as good because of big open space, but they do have a back wall that's very strong, and they have corners. And any of the walls are okay. So the walls are fine. I just wouldn't get in the middle of the room. The odds are nothing's going to come tumbling in, but if it does, that's where it's going to happen. Okay, next to that, you have a glass door in the hallway. That's the entrance to the library. And once you go in the library, immediately to your right is a computer lab. That's smaller than the classroom, so the walls are closer, and you have corners again, and that back corner is against wall. So that's good. Now, just past that, this is on the first floor, so it doesn't quite match up here. There is what I call the reference room in the library. That's where the globes are, the atlases, and the stuff that you just look up. You don't check out any of the books in there, but you just use for references. And that room's pretty good. Okay. Interior room, back wall is soil, and it's a pretty safe place to be. Don't go any further than the library, because then you get on the exterior, and you have windows, and if it is bad weather, severe thunderstorm, stuff like that, then it's going to get blown off trees, come through the glass shattering everywhere, you get hit by the limb, the glass, or whatever. So avoid exterior. So remember, the hallway is only one of those that has emergency lighting. Now, the other thing about going down there, all of you look pretty healthy now, but we're missing a few people. What if they had a skiing accident over the weekend, and they're, going to come in on crutches or on a wheelchair or something like that? we'll probably have to move for that because we don't have a good wheelchair. But crutches, they might be able to get here. But I'm going to be the last one out of here. I'm going to be with that slowest student leaving. So y'all are going down first, and they'll say, "Whoa, bad weather, I better get home and let the dog in," or something. No, don't. You know, dog will take care of it itself. You don't want to be on the road during bad weather. But I will be the last person out, going with that last student, and I will be taking my roll book. And once we get down there below, we all gather together, and I call roll. If we're missing anybody, someone has to go back in harm's way and look for you. So don't be leaving. Don't disperse yourself. Okay. And this is Travis, right? Yes. Okay. Now, I sent the thing, I think it was Thursday evening. Do you know if they got it?
I emailed her this morning, so she emailed me back.
What's that name?
So I emailed her this morning, so she emailed me back and tell me she got it.
Okay.
So
Yeah.
I'll let you know.
I was sort of late. No, actually, let me take that back. It was Friday because I had to wait and check to make sure they're going to let the class run. So I had to wait till Friday when they told me it was thumbs up. Then when I got back over here, I emailed her. So it was late Friday, so she may have been home for the long weekend already. Yeah, so, but hopefully she's got it now. Okay. All right, I'll keep it down. All right, we're talking about safety issues, and we just went over weather safety, go low interior. And you can hear this on today's class. The other type of safety, what's another one? Weather is external. What would be something in the building we have to think of, watch for? Okay, the two things. One would be an active shooter. Sorry we even have to mention this. Back when I first started teaching, I never even thought about the possibility of it because it just didn't happen. Nowadays, it's unfortunately more and more frequent. So what do we do? Now, guess what? I'm hard of hearing. Y'all are not. Y'all are very acute hearers, I bet, okay? You'll probably hear it first. If you think you hear something that could be gunfire, what do we do? Well, one thing is, this door will lock, but only from the outside. There's no key here. There's no button here. I have to go outside. I do have a key for this door. I go outside and lock the door from the outside and don't pull it closed on me. Let me come back in, then we'll pull it closed, and we'll be somewhat safe that way. Except there's another entrance to the room. This door goes into this office here, and this door goes into the next office here, and this door goes into the next bathroom here, and then there's another entrance from the hallway. I don't have a key to that classroom door, okay? This door, I do have a key to, and there is a button here, but don't push this, because this locks from the inside, but not from the outside. That doesn't do us any good except lock us in here, okay? So don't do this one. This door has a deadbolt. I wish I had a key for it. Well, that's a good solid door. I don't, okay? But this door, okay? Now, when I make this door, I'm going to go out there and close the hall door. Turn off the light, because I don't want you to think that one's locked too. I don't have a key for it, so I can't lock it. But I can lock it. It has buttons here. Press that button, it locks from the outside, but not from the inside. So that's safe. We do want to do that. So if I'm occupied doing this, or one of you want to run and do that, close the hall door, and then come in and lock that door with the button. Then close the middle door. The reason for that, he can see in the glass. Okay? If he comes through here, close this door so he thinks nobody's home. Okay? We'll go and close this door too. We won't lock it, but we'll close it because it only doesn't help us. It needs to be locked. I've got this one locked, and then y'all get back here. Joy and Lauren here. Okay? Because he can fire through the glass, he can break the glass, he may be able to fire through the wood. I don't know if this is solid or hollow. I think it's probably solid, but it may not be. He might be able to kick that in, I don't know, or fire through it, but he can't fire through concrete wall unless he has a really powerful weapon, and then if he tries to do that, he's going to get as much stuff fired back at him as, so I don't think it's going to do. That's the place to be. Turn off your phones he won't check the next room, or if he does, he thinks nobody's there either. And then won't try that, but if he does, that will apply. Usually close, it looks like and sounds like nobody's here. That's what we've got to do until we get word from someone in authority that it's okay to move out. Maybe we do move out. And if that we do, we usually go out the quickest and easiest way. And you know that drill, you've probably seen it before. So we'll get the quickest and easiest way next. That's that computer, that's weather. What's the other thing we have to think about? Fire, okay? It's another thing inside the building. So let's do worst case scenario for fire. My computer explodes. Starts arcing and sparking, setting the papers on fire, the books on fire, the desk is wood, so it's set on fire. What do we do? If that were to happen, what do we do? Okay, fire extinguisher. Where is the closest fire extinguisher? Is there one anywhere inside? Y'all checked this out before you came in today, right? Or even last time, right? I didn't listen either. Closest fire extinguisher? 5 feet from where I'm standing. Right there, okay. You can't get much closer than that. So someone goes and gets the fire extinguisher. Now I bet you some of you have always wanted to break that glass out. You know, oh, it looks like up there. This time you get it, okay? And bring it in here. I'll take care of it if you don't want to play around with the fire extinguisher. But that's one thing to do, fire extinguisher. But we don't sit around and watch me put out the fire. What do we do? Anything else we need to do? Okay, we certainly will leave and let the rest of the building, if it catches on fire, they don't. It's up to them. Oh, we need to do a fire alarm too, don't we? Okay. Where's the closest fire alarm? I wish. Okay. This part of the building you see here, the big horseshoe, this hallway here is the old part of the building. Built before fire alarms were required by code. We don't have one anywhere in sight of this room. None of the hallways here. But we did build recently, since I've been working here in the last 20 years, and new addition in the middle here. Now this part here is new. I don't know if they have fire alarms there. But this part I know they do, and that's close. So what we do, and I suggest this is a little bit out of the way, you go with the buddies. It's 2 people go. Okay? Go out the door, hang a left, go down that half flight of stairs, and go to this corridor here and hang a right. When you come through those double doors, this was second floor here, that's a flat corridor. When you walk through the next set of double doors, that set of double doors, you're on the first floor. Okay, I don't know what happened in between there, but it's fine. But anyway, either to the left or to the right, there's a fire alarm. Inside, go to the closest one, pull that. Okay? Then we leave. Y'all be leaving otherwise. If I'm working on the fire, 2 people are doing that, the rest of you get out of the building. Okay? And then when the 2 have that, they get out of the building. And then I'm with the slowest student if the fire didn't start in here. I'm working on the fire if it did, and then I leave the building. And again, when I leave the building, I'm taking my roll book, and if we can't account for you, somebody has to come back into a burning building looking for you. So don't jump in the car and say, hey, building's on fire, no more classes, I'm out of here. Don't do that. Hang around, find out, wait until we get work. Where do we go once we go? Okay, let's do that. Out the door, hang the left, down the half flight of stairs, hang the left, go down a full flight. So this time rather than going in, you don't go into a burning building, you go out. So you go out, and they used to say 75 feet. Now they say, let's go to the parking lot down there. Here, we are in the corner room right up here. We go down that exit right there and go across the green space here to the parking lot down there. It's real hard to see with all the trees leafed out, but there is a parking lot down there. We stay together as a group, even if it's a rainy day like today, until I get there, and again, I call roll. And we wait until we get word. The odds are, well, I don't know, it's hard to say what the odds would be. But that would go for chemical spills, fire, anything inside the building that's hazardous, we get out. We don't have to worry about, oh, one thing we didn't mention And it's important, not just fire extinguisher and fire alarm. We yell 911. We let somebody know, especially if it initiates here. If it starts here, we let somebody know. Better than 911 is if you can get the campus police on this campus, their phone number, and put it on speed dial in your telephone. And I have it in my other grade book. I don't have it in this one. I need to move it here. Then Boston Police is better than 911. 911 is further away. Boston Police will get in touch with 911 immediately, but they get involved earlier. Okay? And if the active shooter started here, somebody's dialing 911 there too. Whether we'll all hear about it together. Okay. Any questions on safety? Sorry, I forgot to do this last time. We had to take class time, but it's better to think of this early rather than wait till the emergency happens. Well, no, you do this, you do, be planning ahead. All right. Any questions on anything? Now, Pratish, is that it? Huh? Pratisha. Okay, Pratisha. Wasn't here last time. We went over the syllabus, we went over the research paper, we went over my office hours, so those have changed. I've corrected that now. We got started in chapter 1. We didn't get very far. Page 5, I think, is all. But let's get back to linear algebra. Any questions on anything, linear algebra or safety or any of the other stuff? And by the way, I do need your paper topics as soon as you can, this week if possible. You can always change if you don't like the topic once you get into it, but get those to me as soon as you can. All right, we got it to page 5, example 4, systems of 2 equations and 2 variables. Okay? Now, you did this, I think, in earlier math courses. 2 equations, 2 unknowns. There's several ways you can do these problems. I think that we mentioned this before. And we're talking linear equations, because this is linear algebra. Okay, so we're only dealing with variables to the first power. Okay, what are 3 techniques you could use to solve 3 equations, 3 unknowns? Anyone remember? Okay. Okay. Sometimes it's called elimination by addition. Okay, which subtraction same deal. Okay. So that's basically where we're going to go in linear algebra. We're going to head that direction. There are 2 other techniques. It works better for 2 equations, 2 unknowns. 3 equations, 3 unknowns, and 4, 5, 5. Hang it up on this. It's substitution. If one of the equations has a variable to the first with a coefficient of 1, you can solve for that variable, plug it into the other equation, and then you have an equation with 1 variable and plug that value together. You can do it that way. That doesn't work for n by n. Okay, so not much reason to think of that. But the third way, and again, this only worked really well for 2x2s, is graphing. You can graph a linear equation, 2 variables, 2 unknowns, x, y coordinate planes, works really well. What would be the 3 possibilities of 2 equations, 2 unknowns on a graph? We talked about this last time too, so 3 possibilities. Okay, they intersect at one point. In other words, anytime those 2 equations, if you wrote each equation in slope-intercept form, if they have different slopes, they got to cross somewhere. Okay, somewhere they're going to cross. Then you'll have a unique solution. Very good. What's another possibility? Second, parallel to each other. Same slope, but different y-intercepts, if you wrote them in that form. They'll never cross, ever. No solutions. Okay? And the third? Same line. Again, same slope, same y-intercept if you wrote them in that form. they pile on each other, and then we have an infinite number of solutions. One unique solution, no solutions, infinite number of solutions. That's our possibility. When you get 3 by 3, 4 by 4, 5 by 5, or anything bigger, you always have those three possibilities. You have a single solution, infinite number of solutions, or no solutions. Okay? The no solutions can take on different ways of happening. Like in 3 space, you can have a plane here, a plane there, and a plane down here. Or in that case, you have infinite number of solutions up here, here, or here. Yeah, so it'll be a little different. Or you could have something that winds up being a line here, a line here. They're not parallel, but they never cross. I mean, they're disjoint lines. Or a plane here and a line up here. So yeah, you could have other things that give you no solution. But you either have a unique solution, infinite number of solutions, or no solutions. Okay. And they give 3 examples here. I see no reason to do any more than just talk about those. So let's keep going. So the number of solutions of a system of linear equations, it either has exactly one solution. And by the way, anytime a system of equations has at least one solution, we call that a consistent system. So one solution or infinite number of solutions, that's going to be a consistent solution. That's a consistent system. If it has no solutions, that's an inconsistent system. Okay? Now, so therefore in the consistent, we could be one solution or an infinite number. If it's one unique solution, that is an independent system. The 2 equations are independent of each other. When they're the same line, then we say they're dependent on each other. One's a multiple of the other. So you get the same line. So you can have consistent or inconsistent. Consistent means you either have one solution or an infinite number of solutions. Inconsistent, no solution. Within these, that you have a consistent system, you either have independent things, that gives you a single solution, independent equations, or dependent gives you an infinite number of solutions. They don't go into the dependent yet, but the 2 consistent, any solution, 1 consistent, infinite number consistent, no solutions, inconsistent. Okay. Now, they show on page 6, solving a system of linear equations. And this is a question. Let me get my pen activated. Okay. X minus 2y plus 3z is equal to 9. Minus x plus 3y is equal to negative 4. And 2x minus 5y plus 5z is equal to 17. There's a system of equations, 3 equations, 3 unknowns. Okay? We don't know, but either it's going to have one unique solution, no solutions, or an infinite number of solutions. Okay, we do know that. We just don't know which it is. Now here is another system of equations. X minus 2y plus 3z is equal to 9. Hey, that looks pretty familiar. That's the first one and the other. Here's the second one. Y plus 3z is equal to 5. And the third equation is just z is equal to 2. Now, which of those two, there are 3 equations, 3 unknowns, which of those 2 systems would be easiest to solve? Or would they be equally hard? Second, much easier. Why? you have one of the solutions. What you can do with z equal 2, plug a 2 in here. And then figure out what y is. Now that you have y and z, plug those in, you figure out what x is. Done! Okay? Now guess what? These are equivalent systems. So if you could ever get it into that form, that's much easier to solve for that one than this one. So the key here, what do you do to get it into that form? Well, that's going to be what linear algebra is, at least the first part of the course is about. How do you go about simplifying this? And that kind of elimination is called Gauss elimination. If you can get it down to one variable, a value for one variable, to plug that in and plug that in, that's called reverse substitution, or back substitution. Back substitution is a better word. Then that's Johann Friedrich, no, what's his first? Carl Friedrich Gauss came up with this method of solving multiple equations, multiple unknowns, trying this, and that's called Gauss elimination. Why did I mention him? He's a potential paper topic, okay? One of the first people you run into in linear algebra. Later, there'll be another guy named Jordan, and we'll talk about another form called Gauss-Jordan. Builds on Gauss and does another way, and Jordan introduced the second part, okay? So let's do some back substitution. And by the way, the book calls this stair-stepping. If you can get it to do that in your variables, when you line them up this way, this is stepping down, that's a good thing to have. So let's do a real easy one. X minus 2y is equal to 5, and y is equal to negative 2. Pretty easy to do. What would be your solution? I know half of it right now. Half of the solution is going to be negative 2. Okay, y is equal to negative 2. What would be your x? Okay, well this would be x minus 2 times minus 2 would be plus 4 is equal to 5. That would be, subtract 4 from both sides, you get 1. So x equal 1. 1, 2. Okay. And it's real easy to check, right? Plug in a 1 and a minus 2. 1 minus 2 times minus 2 is plus 4. 1 plus 4 is 5. Okay. So, yeah. If you can get to the point of Gauss elimination, it becomes pretty easy after that. Okay? Now, the next one is the one we just had, so let's do that one. By the way, 2 equations, 2 unknowns, your solution, whatever solutions you may have, will be in ordered pair. 3 equations, 3 unknowns, that will be an ordered triplet. You're going to have 3 because you have 3 unknowns. You got to have 3. So I can give you the third is a 2. You take it from there. Negative 1 looks good to me. And waiting with bated breath. I hope I'm not holding my breath. Okay. What? Yeah. Take your time. X plus 2 plus 6 is equal to 9. 2 plus 6 is
17.
Anybody else? There's a pluses here. X plus 2 plus 6. X plus 8 is equal to 9. X had better be 1.
I thought that top number was a 5.
Oh,
This had
This
five?
one,
where? Oh, that? I'm sorry.
You're 9 on the top.
Okay, sorry about that. Making fun of my writing. I'll remember that with great time. No, I'm just kidding. Okay.
I thought it was a nine.
Oh, so it is a 9. Okay. Well, let's try it and see. Let's check it and see. 1 minus 2 times minus 1 is plus 2. 1 plus 2 is 3. Plus 6 is 9. Negative 1 plus 6 is 5. And 2 is that works. Okay. Could be a long term. No, I'm just kidding. Okay. All right. Now, they either showed us that it was an equivalent, or told us it was an equivalent system, or just gave us some pretty easy systems. That's not what this course is going to be about, is it? Not just giving you the easy ones. It's going to be, how do you get those equivalent systems? Okay? Here are the 3 operations. Still no books, right? So let me write all this down. Everybody got this? I can erase it. Okay. Here are the 3 operations you can do to produce equivalent systems. Okay? Now, what you have is 3 equations, or 7 equations, or 15 equations, and so many unknowns. It doesn't have to be the same number. We like for them to be, but it doesn't have to be. So multiple equations, multiple unknowns. Okay? Here's the first thing that you can do. Doesn't matter at all. Interchange any 2 equations. That's not going to affect your answer, is it? If you write the equations in different orders, same system, right? So you can always interchange any 2 equations that you want. Okay? Doesn't change your result. Now, second thing you can do. Multiply any equation by a non-zero number. Now that doesn't quite seem fair, except, remember, you're multiplying the whole equation. Something that's legal. Multiply everything on both sides of the equation by a non-zero. Don't ever go around multiplying by 0, okay? What do? You lose all meaning of your equation. 0 equals 0. Big deal, okay? That's not very much fun, okay? And by the way, never go around dividing by 0 either, okay? You can't do that either. But you can multiply or divide any equation by any non-zero number, okay? Because as long as you multiply both sides of the equation, you got it. It's fine, okay? Now this next one is not quite so obvious, but it is a legitimate thing. Add a multiple of one equation, I'm going to abbreviate, to the other equation. I'm going to put another equation. Now, if you think about it, that's what you were suggesting to begin with, right? You multiply, so when you add them together, you eliminate one. That's called elimination by addition. That's what we're doing here. If you multiply one equation by, both sides of the equation by something that's legal, add it to another one, you're going to get an equivalent one. And back when we were doing 2 by 2, so I think I will go back and do at least one of those, just as a memory enhancer. Okay, this one. X plus y is equal to 3. And x minus y is equal to -1. Okay? Now, you don't have to multiply by anything. If you just add these 2 equations together, you lose the y's, right? So therefore you get 2x is equal to 2. X equal 1. You then plug back in, x equal 1, you back substitute. Got it on, right? Or you could have multiplied this equation by -1 and then add them together. And that would give you 0 here. And this would give you 2y is equal to 4, because multiplied by -1, so it goes plus 1. If 2y is equal to 4, y is equal to 2. Okay? So, what did I say the first one was? 1, 2. 1 and 2 is 3. 2, 1. 2 minus 1. No, 1 minus 2. Yeah. 1 minus 2 minus 1. Yeah. So, yeah, that works. So, what you did was add a multiple of one equation to another equation. That's perfectly legal in most states. Okay. So you can do that. So those are the 3 acceptable operations to do. All right? Now what we're going to do now is actually solve one using those. And we'll begin our process of doing it sort of smartly. Now, did y'all do this in an earlier course? If you did, I don't need to go over it. But did you do many 3x3s? Most of the time when I've taught it, I've stuck with 2x2s and maybe only one example of a 3x3. So, okay, let's do a 3x3. X minus 2y plus 3z is equal to 9. Okay? Minus x, you've seen this before, by the way, plus 3y is equal to minus 4. This is one we had earlier. 2x minus 5y plus 5z is equal to 17. That was one we did before. And when I said, which is easier to solve, this one or the next one? You told me the second one. This is that first one. So basically what we're going to do, we're going to do the steps that we just talked about to get to the second one. So I'll take at least 2 steps. Okay? Now, I'm going to start by giving you what I want it to look like. Okay? Now, they're not doing this yet, but I see no reason not to. Okay? Remember, we stair-stepped it down this way, right? So what we're trying to do is eliminate things underneath that. So the best and the easiest way is to get this first one to have a coefficient of 1. Now this one, the first one, already has a coefficient of 1. If it didn't, if this one was here, that one's there, or this one was here, if it was any other arrangement, the first thing I would do, I would flip them to get that 1. Okay? Now if none of them are 1, then we go to a different effort. Okay? But if you have one of these that starts off with a 1, get it in that position. We already got it there. Okay? So now it becomes pretty easy. What we're trying to do is eliminate the x's in these two. And this one's real easy to do. What do we do? Add equation 1 to equation 2. And that's going to eliminate our x here. So we leave the first one just like we had it. X minus 2y plus 3z is equal to 9. And the second equation is now adding a multiple of the first to the second. The multiple is just 1. So add those two together, and what do you get? X minus x is 0. Okay? Minus 2y plus 3y is y. Why not? Okay? 3z plus 0 is plus 3z. And then 9 minus 4 is 5. Okay? Now, I welcome you to go back and look on the previous page, and you'll see the second equation is y plus 3z is equal to 5. That is equivalent. Okay? Now, it's going to take a couple steps here. What we're going to do now, we're again wanting to eliminate the x. Remember elimination by addition? So what should we multiply the top? We're using the top equation, that 1 is the coefficient there, to eliminate this one. So what would we have to do? multiply the x by -2 and add to this, right? Won't that work? So I'm going to write this as minus 2e1, that's equation 1, plus e3. That's what we're doing. The whole equation that way. So minus 2 times x is minus 2x, plus 2x is 0. It's disappeared. Minus 2 times a minus 2 is plus 4, plus 3 is 7. Right? 7y? No. Sorry, I botched up. I did the wrong equation. Minus 2 times minus 2 is plus 4y. Minus 5y is minus y. Okay. So this isn't looking too good. Okay. Minus 2 times plus 3 is minus 2 times plus 3 is minus 6z plus 5z is negative z equal minus 2 times 9 is minus 18 plus 17 is negative 1. Okay. Now, we got our stair step started. What we want to do is eliminate this one. So we'll have everything there. All right. So what might we do? We just add equation 2 to equation 3, right? So equation 2 plus equation 3 is going to be our new equation 3. Okay? Leave the first one alone. X minus 2y plus 3z is equal to 9. That's a 9. Okay? Y plus 3z is equal to 5. Okay? And then if you add those two equations, bottom two equations, what do you get? 0. Second, 2z is equal to 4. Now, what can you do to the last equation to get, oh, and by the way, notice what we do. We like to have, just like I said before, we like to have this coefficient 1. We like to have this coefficient 1. It just came out that way, so we were lucky. This one didn't come out 1. It came out 2. So what do we do to change it, make that coefficient 1? Divide by 2, or multiply by 1/2, right? That's the same. So divide both of those by 2. So equation 3 divided by 2 becomes the new equation 3, and that becomes z equal 2. I'm going to write it again. And now if you look back to the previous page, that was our third equation. And we're stepping down just like they said, and we back substituted, and remember what we got? It wasn't easy, but we got it. An ordered triplet. The last one was 2. Okay, in that order? 1 and negative 1. Okay, that sounds right. Yeah. Is that right? Yeah. Minus 1 plus 6 is 5. Yeah. Okay. Yeah. Got it. So, that's how we do Gauss elimination of 3 equations, 3 unknowns. 7 equation, 18 unknowns. I mean, whatever you got there, you do this kind of process. Try to get it to stepping down like that. Using those 3 things, interchange any 2 equations, multiply any equation by a non-zero number, or adding a multiple of one equation to another. Okay, which we did right there. Okay. So we got 1 minus 1, 2. Exactly. Now they show the graphic of this And it is correct, but boy, they got these two planes awfully close to being the same, but they're not quite the same. So you do have one unique point. By the way, I'm not going to ask you to draw graphs of planes and show that, just like graphing two equations, two unknown, to me is the hardest way to do it. Elimination by addition, sometimes substitution, easy way to go. Okay. And just like we did before, we could go back and check these, and I think we did, didn't we? 1 plus 2 plus, yeah, we checked all those. Always a good idea to do. Okay. Now, what were our three possible results? This one we had one unique solution. Second, no solutions, or infinite number of solutions. Okay. I think I'm going to start my page afresh. Is that okay? Here's another system of three equations, three unknowns. X1. Now this time they're not using X, Y, and Z. They're using subscripts for X. X1 minus 3X2 plus X3 is equal to 1. 2X1 minus X2 minus 2X3 is equal to 2, and X1 plus 2X2 minus 3X3 is equal to minus 1. Okay? Now what do we like to have happen to the very begin? Yeah, the coefficient 1 in the upper left corner. We got it already. We don't have to move anything around. If that had been a 3 up there, we could flip equation 1 or equation 3, exchange any two equations, get that one over. But we started off that way, fine. So what do we do next? What we'd like to happen next is this down here to have a coefficient of 0, right? Because we want that 1. So how we would make that a 0 using that first equation? Negative 2 times the first equation plus the second equation will make that a 0. Okay, so let's do it. Negative 2 equation 1 plus equation 2. Okay? So we're using the first equation, leave it alone. X1 minus 3X2 plus X3 is equal to 1. Oh, by the way, we had a little blurb on Gauss there. I had mentioned them. Let me just mention Gauss. He is usually recognized along with very ancient Archimedes and that little guy Isaac Newton who developed calculus, and Gauss are usually considered the three greatest mathematicians in history. That's pretty healthy company. Archimedes, way BC, and he still came up with a lot of things no one had conceived of and we still use. And Newton developed a whole new branch of mathematics, calculus, and then you have Carl Friedrich Gauss. And then a fairly interesting point. Although this method was named in his honor, the Gauss method, the Chinese had used it, an identical method, almost identical method, 2,000 years before Gauss. But he didn't hear anything from the Chinese didn't hear anything from him. They were way ahead of us on this thing. But we're Western-centric, so we don't recognize that. And by the way, there are quite a few very brilliant Indian mathematicians we don't know anything about either, okay? And probably others in other cultures that their work never got published, and they may have been doing things that we could not have conceived of either. But anyway, That's good. All right, so I write down the first equation, and then let's multiply the first equation by -2 and add to the second, and what do you get for the first coefficient? -2 times 1 plus 2 is 0. -2 times -3 is plus 6 minus 1 is 5x2. Minus 2 times 1 is -2 plus another -2 is -4. x3 is equal to, you have to multiply this side too, -2 times 1 is -2 plus 2 is 0. Now, we weren't trying to eliminate anything there, it just happened to do. Okay, what else do we want underneath that? We want a 0 down here as well. And again, using the first equation and the third equation, what do we do to make this number 0? Okay, yeah. Third equation minus the first equation. That was just another way of saying that is -1 minus equation 1 plus equation 3. Okay? So let's do that. Minus equation 1 plus equation 3. Okay, so just do that. -1 plus 1 is 0. Negative of -3 is positive 3 plus 2 is 5x2. Yay or nay? Okay, and then minus a minus is plus, minus a plus is -1, minus 3 is -4, x3, and -1 plus a -1 is -2. All right. Now, you can first look at these two. Does anything make you say, wait a minute? Absolutely. You use the right word too. That's not consistent. You can't have the same thing on this side, identically the same thing on this side, equaling something different on that side. Can't happen. Okay? So therefore, this is an inconsistent system. I don't know if you meant it that way, but that's exactly right. There is no solution. None. This is one of those no solution. Now, if this were two equations, two unknowns, they'd be parallel lines. They don't have to be parallel here or parallel planes. They just don't. It's inconsistent. It can't happen. There's no way you can do the same thing to two numbers and have one answer one time and another answer a different time. Just impossible. So this is how it's going to look when you have an inconsistent system. Now you could have taken it one more step and said you want this to become a 0 down here. I'm forgetting about the 5. So do a minus equation 2 plus equation 3. And that'd be -5 plus 5 is 0. Plus 4 minus 4 is 0. And 0 equals -2. And when is that true? Never! Okay, you can't ever have 0 equals -2. So anytime you come up with a situation where it's impossible to happen, inconsistent system. Stop right there, inconsistent system. Okay? And they carried it that next step in the book. Now they show the figure here, and again, I don't get a lot of warm jollies out of this one, because I can't quite follow it. Y'all don't have your book, so I'll do my best. I'll turn back to the previous one, and that's not an easy one to do. By the way, anytime you have this kind of stuff here, each of those represents a plane. It would be a straight line in 2 space, but it would be a plane in 3 space. And that first one had one unique solution. You have a pink plane that goes like this, a purple plane like this, and a green plane that goes like this. and the pink and green crossing the line here, the pink and purple crossing the line that's back there, and they both cross there, or the green and purple crossing the line. Well, that's the green and purple. But anyway, it's only one point of intersection. And again, they had to pick planes that were so close together it's hard to see. Now this one, the pink plane is like this. It intersects the line with the green plane right there. The purple plane's here, it intersects the line, and those two lines are parallel to each other. That's why you have no solution. Okay? Those two intersecting lines are parallel. Again, they drill so close together it's hard to see, but indeed they're not. Okay? Now, let's do another. So, when you have a unique solution, one answer, you're going to come up with a unique x equal this, y equal that, x1 equal that. Each one's going to have one and only one solution. When you have no solutions, you eliminate your variables and you have one number is equal to a different number, which can't be the case. Or some combination of variables that are identical equaling the things that are not identical. Not possible. So those are your no solution, inconsistent system. Okay, let's do this one. x2 minus x3 is equal to 0. x1 minus 3x3 is equal to negative 1. And negative x1 plus x3 plus 3x2 is equal to 1. Okay? It's a little bit wrong with this one. What's like we don't want it to be. What is our ideal situation? Upper left coefficient of 1. This has a coefficient of 0. Not like I like it. So what might we do? Yeah, flip those two. We can rearrange the order. First thing we're going to do is flip the two. Equation 1 and equation 2 exchange places. Okay? So now we have x1 minus 3x3 is equal to negative 1. x2 minus x3 is equal to 0. You have to do the whole equation. And minus x1 plus 3x2 is equal to 1. Okay? So now that we got that 1 up there where we want, the coefficient of 1 in the first one, what do we have to do? Next thing we want the 0 below. We already got it. Done. Okay? It was given to us. And then we want a 0 down here. How do we get that? Like that. Add equation 1 to equation 3. Exactly. So equation 1, plus equation 3. Okay? So this is going to give us x1 minus 3x3 is equal to negative 1. Leave the second one alone for now. x2 minus x3 is equal to 0. That's stepping down just fine. And then we add these two together, and what do we get? 0. Now, unfortunately, you get a 0 plus 3x2 is 3x2. And add, where is it? There it is. Add, 1 to 3 here, and you get minus 3x3. And that's equal to 0, right? Okay. Now, what might we do next? Well, first we have what we want. We wanted a coefficient of 1. Here we got it, and 0 below it. Fantastic. Next, we want a coefficient 1 here. We got it. We didn't have to do a thing to get it, right? Okay? And we want a 0 below it. So how do we get this 3 become 0? Using the second equation. Negative 3. Add it to that. Right? Subtract it, yeah. I think you'll find that these get bigger and bigger because subtraction, you know, and sign numbers and stuff, I tend to make more errors that way. So adding, I'm a little more precise on that, you know. So change signs and add, yeah, it's the same thing, but if you change signs to begin with. So how about negative 3 equation 2 plus equation 3? Okay. We'll leave the first equation alone. X1 minus 3x3 is equal to negative 1. Here's the hardest thing about linear algebra. I'm going to write down all this stuff over and over and over and over again, but unfortunately it's part of it. We're going to eliminate some things in a minute. It's going to get better. X2 minus x3 is equal to 0. Okay? And then once you do that step, minus 3 equation 2, that would be minus 3 times 1 is minus 3 plus 3 is 0. Minus 3 times a minus 1 is plus 3, minus 3 is 0, and 0 plus 0 is 0. Oh boy, isn't that neat? 0 is equal to 0. When's that true? Always. Okay? So what does this mean? Infinite number of solutions. Not just a single solution, infinite number. It doesn't mean any values you put in there, but anything you put in to make the first equation true is going to make the first and the second equation would automatically make the third equation true too. In other words, there's an infinite number of solutions. Not just a single unique one. Not just none, but infinite number. Okay? So that's your third case here. Now, here's what we usually do with that. Here's how we write. Again, it's not any three numbers you just happen to throw out there, but because x3 you don't get a value for it, what you usually do is say let t equal x3. Okay? That's called a parameter, t. Anything. Let it be anything. Okay? Then, doing Gauss elimination, basically, if you put t for x3, here you have x2 minus t is equal to 0. Well, what does that make x2? T also. Then x2 is also equal to t. So maybe I should have put x3 equal to t. It doesn't matter what order. Well, let's go on above here and say then x1 is equal to what? Well, x1 minus 3t is equal to, this drives me nuts, minus 1, right? Just plugging that in. That gives you x1 is equal to 3t minus 1. Okay, so your ordered triplet is 3t minus 1, t, t. Pick a t, any t in the world. My favorite is 0, okay? Then this would be minus 1, 0, 0. Well, does that work? Am I on the right one? No, this one. 0 minus 0 is 0. Yeah, that works. That would be a minus 1 plus a minus 0 is minus 1. Yeah, that works. And a equals 0 would be a plus 1 plus 0 is plus 1. Yeah, that works. Okay? But any t you put in there. 5,435 pi. You could do that. I'm not going to. Put any t you want to in there and do this one, this one, this one. You're going to get a solution for any t you happen to choose. I usually stick with easy numbers. 0, 1, -1, 2. But they'll work. That's your infinite solution. That's a consistent system, but your equations are dependent on each other. Now, I don't think they show you a graph of that one, so I can't do that. Now, there's a little discovery thing here. I don't really see a purpose for this, but let's just do it. X minus 2y is equal to 1, and minus 2x plus 3y is equal to -3. Now let's use Gauss elimination just like we did before. What do we like to have first? 1 in the upper left, we got it already. Thank you very much. Okay. Next, we want to 0 below it. How do we make that become a 0? The top one by 2 added to the second, right? So 2e1 plus e2. What does that become? We're going to leave e1 alone. X minus 2y is equal to 1. So doing that, you get what? 2 times 1 is 2 minus 2 is 0. So that goes to 0. 2 times -2 is -4 plus 3 is -y. And 2 times 1 is minus 3 is -1. Okay? Now, what do we like having next down there? Prefer for that to be a plus 1. So how do we make that become a plus 1? Multiply or divide both sides by -1. Okay? Which, watch my sleight of hand. Done. Okay? Well, done completely. So y is equal to 1. And what is your x? Wait, let me not put the equal. I tend to do that myself, but let's not do it until you get more used to it. Okay? X minus 2 is equal to 1. So x is equal to 3. Good. All right. So you get x equal 3, y is equal to 1. Okay? I don't know why they wanted you to do it, but they did. Okay. Y'all have books yet? Are you planning to get books or e-books or rent a book or do something? Because I give homework assignments from the book. If you have another linear algebra book and have a section like this, you pick your own problems to do. But in this one and in this thing, the odds are given in the back. And by the way, this author, Ron Larson, does something that I haven't found any other author that does on all the exercises. In addition to having the answers in the back, he has, and it's written here, see www.countchat.com for worked out solutions to the odd number exercises. So when you work these exercises, then check your answer in the back. If you see it's a different answer, see if you can figure it out, but don't get too tied up with it. Don't get too distressed and in knots and stressed out about it. You can always go to countchat.com and see how he did it and say, oh, okay, I see where I made my mistake. But I think it's useful to try to figure it out on your own, but don't get super frustrated with it. Before you reach that point of frustration, go to CalcChat.com and see how we got it. Otherwise, you have to wait till you see me the next time and say, can you do this problem? And I'll be glad to do it. I'll still be glad to do any problem that's in the book. But if you're doing your homework, that's why I assigned an odd number exercise. You have the answers in the back, and you can go to CalcChat.com to see if you can't figure out how to get those answers. So any of the odds 1 through 5, any of the odds 7 or either 7 or 9 or both, any of the odds 11 through 23, any of the odds 25 to 29, any of the odds 31 to 35, any of the odds 37 to 55. There's a whole passel of them there. Some of those are 4x4s even. Okay? Any of the odds 57, either 57 or 59 or both. Either 61 or 63 or both. And then there's a word type problem that 65 would be a good one to do. And then there's a true false, 67. It has 3 parts. And then there's a 69 that you can do if you want to. That doesn't have a special characterization. Then do either 71 or 73, 75, any of the odds 77 to 81, 83, and then there's a writing type exercise. You don't have to write it, but if you want to think through it, you can. That's 85. And then there's a show that this is true for 87. And then there's an 89 and a 91. Now, those toward the end are a little more abstract. You won't see these on the test that I can remember. But if you find this interesting and want to just take a little more challenge, you can go with that. All right, so that's section 1.1. All right, ready to start 1.2. All right, I'm going to leave that. Oh, man. Okay. Here was a system of equations, right? I said one of the most tedious things about linear algebra is having to write down so much over and over. Now, you're still going to have to do it, but I'm going to give you something that's a little bit easier, okay? Why don't we just forget about the variables at the beginning and then put them in at the end where we need them, okay? Because we really aren't doing anything with them, just carrying them along. But anything, okay? So let's just deal with the coefficients. So if we wrote this with just coefficients, that would be 1, -2, 1. -2, 3, -3. Okay? Now what I've just written is called a matrix. It's an array of numbers. Okay? Now you could have some letters in there too if there was an unknown something another in there, but you've just eliminated the variables. Okay? Now, in my old days, I like to draw a dotted line through here just so you separate the variable part from the constant part. In other words, those are your equal signs. But this book doesn't do it, and sometimes I found when I do put a dotted line there, you might confuse that for another 1 in there or something like that. So rather than making more confusion, just remember. Okay? And then we're going to use Gauss-Jordan elimination without the variables, just using this. And guess what? We like having a 1 there. Oh, and by the way, when you have this matrix, an array of numbers, you can exchange any 2 rows anytime you want to. That's equivalent to exchanging 2 equations, right? You can add or multiply any row by any non-zero number anytime you want to. Or you can add a multiple of this row to that row and come up with a new second row anytime you want to. Those are the same three accepted operations you had with equations, you do them with rows. Okay? So let's do that. You have a 1 right there where you want it. Okay? Now, what we're going to do is try to get this to be a 0. Right? How do we do that? 2 times row 1 plus row 2 now becomes the new row 2. Just like we did with equations before, now we're just dealing with rows. Because those represent equations, right? Now we don't mix up the numbers because the columns represent the variables. We make sure those are in line. And the equal sign is that dotted line I used to put in there, so all your constants are on the outside. So we write down the first row again, 1, -2, 1. No getting away from that. You have to repeat a lot of writing here, but at least you don't have to write the letters as well. And what happens when you multiply row 1 by 2 and add to row 2? 2 times 1 is 2, plus or minus 2 is 0. Now we put in zeros. Before we just left them blank. 2 times minus 2 is? Minus 4 plus 3 is? Minus 1, right? 2 times 1 is? 2. Minus 3 is? -1. Okay? And now, what you want? You have a 1 here, 0 below it. You want the first non-zero entry in row 2 to be a 1. It's a -1. So what we do? Multiply minus row 2 becomes row 2. In other words, multiply -1 by that. Or divide, but it's easier to multiply. There, I did it. Okay? Done. Now, what does this mean? The second row is the y row, so this is y is equal to 1. And then you have x minus 2y is equal to 1. So x minus 2 times 1 is equal to 1. So x minus 2 is equal to 1. X is equal to 3. There's x equal 3. There's y is equal to 1. X equal 3. Y is equal to 1. You go back and put your variables in at the end. You took them out at the beginning, put them back at the end. See how it worked? So it's a little bit easier just using the coefficients, not having to carry around all the letters. Okay? But you need to put them back at the end. Where you took them out at the beginning, put them back at the end. Second column was always your y's, first column was the x's. Make sense? All right. So, what's the definition of a matrix? If you have M and, I better write this down, I guess, because y'all don't have your books. Okay. If M and N are positive integers, okay, then an M by N matrix, okay, is a rectangular array okay. Now here's how we usually express it. A11, A12, A13, ... A1, N. Yeah. A21, A22, A23, ... A2, N. A31, A32, A33, ... A3, N. ... A M1, A ... A M2, ... A M3, and a ... and a ... and everywhere ... every, okay. to AMN. Okay? And typically a matrix we put square brackets around. Okay? What this means, you have M rows in columns. See? 1, 2, 3, 4, 5 up to M rows. 1, 2, 3, 4, 5 up to N columns. Okay? And you always, the order matters. The first is the number of rows, the second is the number of columns. Now, the individual elements in here, you just look at it and see. A sub 3, 2 means you go to the third row, second column, that's your number that's there. Okay? So these are just identifiers, labels, that tell you where to go in the matrix to find those. The nth row, fifth column, that would be somewhere over here. The 14th row and the third column would be right there. Okay? So that's what your identifiers are. The matrix is M by N, M rows, N columns, and then each entry has two number address, the first number being which row it is between 1 and N, 1 and M, and the second subscript is which column you're in, something between 1 and N. Okay. Now, in general, we could say this is the matrix A sub ij, okay, where I is anywhere from 1 to M, and J is anywhere from 1 to N. Okay, so you can write the whole matrix as A ij, where I goes from 1 to M, and J goes from 1 to N. Okay, that's really shorthand notation. Okay. The size of the matrix is N by M, always number of rows by number of columns. When M is equal to N, we call that not a rectangular array, but a square array, a square matrix. Square matrices have some important characteristics we'll run into later. Okay? When you have a square matrix, okay, that M is equal to N, then you have a diagonal that's unique. But it's a diagonal going from upper left to lower right. That's called the main diagonal. M is equal to N. Okay? And that is a unique diagonal. Okay? Anything could happen other than that, but that's a unique diagonal. Okay? Or the main diagonal. Okay? So, this is incredibly easy stuff, but it's important you get it. Okay? Here is a matrix. Believe it or not, that's a matrix. What's the size of that matrix? What's the dimensions of the matrix? 1 by 1. Okay, only has one element, the 1, 1 element, so it's 1 row, 1 column. That, believe it or not, is a matrix. Okay? How about that? It's a 2 by 2. It happens to also have a name, the zero matrix. The 0 2 by 2 matrix. Every element in it is 0. Okay? Why they threw that in there, I don't know, but it's a 2 by 2. Okay? How about this one? What's the size of that matrix? I mean, the dimensions of the matrix. 2 by 3. 2 rows, 3 columns. What do you notice about this one? They're not all integers, okay? In fact, they're not all rational numbers. There are irrational numbers in there. E's an irrational number, pi's an irrational number, square root of 2 is an irrational number. You can have positives and negatives, you could have fractions or decimals, you could have any real number. So far, and we won't in this course, deal with any complex numbers in a matrix, okay? It can happen, we're not going to do it. In fact, we're not going to have many that have irrational numbers. Some of your homework exercises, if you were, no, you couldn't see them because you don't have the thing, definitely had fractions in the matrices. That makes for a little messy stuff, but there are some ways you can make it better. Irrational numbers are always messy. Complex numbers would be even worse. Okay. Now y'all have to watch out for time because I get carried away and just keep on talking. In my last class, 2 people were coming back to this one, so I have a pretty good idea. This one, none of you are coming back for my next one, so I don't think, right? None of you are doing physical science, so don't let me keep going until people pile up outside. I need a little break myself. Okay. Now, I did it a moment ago when I had the numbers from the previous section on the screen. I'm going to do it again more formally. Here's a system of equations. X minus 4y plus 3z is equal to 5. Minus x plus 3y minus z is equal to negative 3. 2x minus 4z is equal to 6. Now, we basically did this before. I didn't make a big deal about it. But when I'm doing it here, I want to sort of make a big deal. When you have a system of equations, there's nothing that says you have to line it up this way. But before you start dealing with matrices, be sure you line it up this way. I mean, a system of equations could have been the first 2 equations just like they are. The third one could have been written as minus 4z plus 2x is equal to 6. Okay? Written that way. But before you start dealing with it, get it ordered. So your equations are where they belong, your variables are under the variables, and your equal signs under the equal signs. Make sure that everything is blocked out the way it's supposed to be before you go. Now, what we're going to do is basically take out the variables and write this as a matrix. Excuse me. Okay. Poor people at home weren't expecting that, were they? Okay. What would be the matrix represented by that? 1, negative 4, 3, 5. Negative 1, 3, negative 1, negative 3. 2, 0, negative 4, 6. Okay. Now, this is called an augmented matrix. And you might say, why do you say augmented? Because it represents a system of equations, 3 equations, 3 unknowns, but you have a 3 by 4 column here, a 3 by 4 matrix, because you've augmented with the coefficient matrix with the constant row or column and made it an augmented matrix. Okay? Like I said, in the past I used to do a dotted line down there because one of the early books that I studied under, that's what they did, but they seem to be getting away from that, so I'm not going to go back. But this matrix here, without the 4th column, is called the coefficient matrix, because that's the coefficients in here. You augment that with the constants and make it the augmented matrix. Okay. Now, the reason that's kind of important is because your coefficient matrix is a square matrix. Remember, that was special. And there are some characteristics that come with square matrices. Okay. The augmented matrix then, for 3 equations, 3 unknowns, it's never going to be square. It's going to be rectangular because the extra column is put at the end. Now, if you wanted to start solving this system using the matrix instead, do the same things we did before. You can exchange 2 rows. You don't need to here. You can add or subtract, multiply or divide any number by any row. In fact, one of the first things I would do on this, look at that last row. 2, 0, negative 4, 6. What do you notice? All even numbers. You can divide it all by 2, which is multiplying by 1/2. So I would, first thing I do is make this a 1, 0, negative 2, 3. Okay? And that makes the whole rest of it easier. Okay? I mean, maybe not, but at least the smaller the numbers you can deal with before you get into fractions, okay, usually the better. Maybe not every case, but better. So that's what I do. They're not asking us to do anything with that, but that's just giving you an example of a coefficient matrix, the square matrix, augmented with the constant column, and that would be the augmented matrix. So again, I don't think I need to write it down again. What is now? Before we called them the accepted operations, I believe is what we called it, wasn't it? Let me go back and find operations that produce equivalent systems of equations. Now what we call these are elementary row operations. Operations you can do the rows of a matrix. The easy things you can do, okay? Exchange 2 rows, multiply 1 row by a non-zero number, or add a multiple of 1 row to another row. Those are your 3 elementary row operations, just like we did. And what we'll have then is a new matrix, but we call it row equivalent. The rows are equivalent to the previous one, usually in a simpler form. Okay? So, let's try to do example 2 on page 14. Here's example 2. The A part. 0, 1, 3, 4. Negative 1, 2, 0, 3. 2, negative 3, 4, 1. Now, if you were messing with this one, based on what we've done before, what would be the first operation you would do? 1 and 2. I would too. You don't have a 1 anywhere, but a -1 is pretty easy to change to a 1. So that's exactly what I would do. So what we're doing is row 1 and row 2 get exchanged. Okay? So the new matrix would be what? Negative 1, 2, 0, 3. Next. 0, 1, 3, 4. Next. Perfect. Okay? That is an accepted elementary row operation that gives you that. Okay. Now, I don't see any reason to do the B part. Let's go on and work on this one. What would be the next thing you would want to do to that one to get it like you would like it to be? Second? Multiply what?
Row 3, row 2, multiply by 2.
Okay. Say it again. Multiply what by 2?
Multiply row 2.
Okay.
To then add.
Row 2. Okay. This row 2? The new row 2? There's your row 2 here. Multiply that by 2 and add it to row 3. That's not going to clean up anything, because that will still be a 0. That'll be a 2. That'll be a 2. And that'll be a -1. So basically, start with that upper left. Is that what you want it to be? Yeah, you want it to be positive. So what might we do to that first row? Either multiply or divide by -1. Exactly. So what I would say, it's easier to write this way, minus row 1 is the new row 1. That's the legal move. Exchanging 2 rows or multiplying by a non-zero constant. So this one would be, what would that be now? What would it be? 1. Second? -2, 0, -3. And the rest stay the same. 0, 1, 3, and 4. And 2, -3, 4, and 1. Everything else stays the same. Okay? Now, what's the next thing you would like to happen here? You got a 1 in the upper left. You got a 0 below it. And what would you also like to have? A 0 below that too. So what might we do to make a 0 instead of the 2 there? Say that again. The top row by -2. -2 row 1 and add it to row 3. And that becomes the new row 3. Whoops. Okay. My writing stinks. Okay, so you leave row 1 alone. 1, -2, 0, -3. Leave row 2 alone. 0, 1, 3, 4. And now what's your new row 3? 0. Second. +4 minus 3 is 1. Okay. Next. 4. Next. A little louder. No, I don't think so. +1. -6 plus, no, it's not -6. It's +6 plus 1 is 7. Okay. Now, one thing about linear algebra, all the operations are pretty simple most of the time, multiplying and adding. But they're really fraught with opportunities to make mistakes, so be very careful. Take your time and do them. Okay, now what do we want next? We have a 1 here, 0 below it, and the next thing we want is a 1 here. We already have it. And now we want a 0 below it. And how do we get that to happen? Negative row 2 plus row 3. And that becomes the new row 3. Okay? So, we leave the first line alone. First row alone. It's just like we need it. 1, -2, 0, -3. Okay. Leave the second row alone. That's the one we're using. 0, 1, 3, 4. And what's the new third row? 0, 0, 1, 3, you said? You know, I think we have it now. If you go back and think where this came from, oh no, we didn't have it. Okay. If indeed this represented an augmented matrix, we don't know that it did, but if it did, then your x sub 3 is equal to 3, and you can go back and plug in x sub 2 plus 3 times 3 is 9 is equal to 4, so x sub 2 is equal to -5, and then x of 1 minus 2 times minus 5 is plus 10, plus 0 is equal to, I think that's a minus 3, isn't it? Negative 3. So x of 1 is equal to minus 13. There you have it. If that was, it doesn't have to be. That was just a matrix. We didn't know that it represented a system of equations. But if it did, that would be your solution. Okay? So you see, we used all the operations. We exchanged two rows, we multiplied a row by a non-zero constant, and we added twice. We added a multiple of one row to another row. Okay? Now, yes, time. Thank you. We'll begin next time on the B part of that problem. And let me also erase that mark, because that was the last time I taught the course, or some previous time. And homework exercises here. We didn't get very far in this section, but I know you can do any of the odds 1 through 5. This is on page 22. And I'm pretty certain you can do either 7 or 9. And any of the odds 11 through 17, I think. And we'll stop there. And we'll wrap it up later. All right, any questions? Good deal. We'll see you on Thursday. And let's see, we started out with 5 out of 6, and we have 5 out of 6 today too, but it's just a different 5 out of the set 6. So hopefully Audrey will be back next time. All right, good deal. All right, then we'll see you Thursday. And thanks.